Why and how does language translation using AI work? Language translation through AI relies on the idea that languages, though diverse in structure and vocabulary, share patterns that can be learned by machines. But how can a computer recognize these patterns? And more importantly, how can we train it to turn a sentence in English into the equivalent in French, Spanish, or Swahili? The goal is to build a system that understands language as a sequence of context-aware tokens and learns to map between different language structures. Here's what we're going to explore. You'll learn how to build a basic machine translation model using Python. The journey will walk you through understanding data collection, pre-processing, model design, typically sequence to sequence using recurrent neural networks or transformer architectures, training, and evaluation. You won't build a GPT-like model from scratch, but you will build something foundationally similar on a smaller, more graspable scale. The very first step in training a translation model is getting a data set that contains pairs of sentences, one in the source language and its translation in the target language. This is called a parallel corpus. Start by finding a data set like the Tatuba project, Open Subtitles, or the TED Talks translation corpus. These contain aligned sentences in 2 languages. Download the dataset and load it using Python. You can use tools like Pandas or simply read the lines directly if it's in plain text. Make sure you separate the source sentences from the target ones cleanly, keeping sentence pairs aligned. Cleaning and pre-processing text. Machine learning models don't understand raw language, so you'll have to prepare your data. Lowercase all text to reduce vocabulary size. Remove any unnecessary symbols, accents, or HTML artifacts. Tokenize each sentence into words or subwords. You can do this using libraries like NLTK, Spacy, or Hugging Faces tokenizers. Next, build a vocabulary of the most frequent words. Assign each word a unique integer ID. For words that don't appear in the training set or are too rare, use a special token like UNC. Add tokens like SOS for start of sentence and EOS for end of sentence to help the model understand where sentences begin and end. Finally, pad all sequences to the same length using pad tokens so that your model can process them in batches. Designing the model architecture. There are 2 common ways to design a translation model: using a sequence-to-sequence model with recurrent neural networks, or using transformer architectures. For a simple start, go with a sequence-to-sequence model using an encoder-decoder framework. The encoder takes the input sentence in the source language, processes it through an embedding layer followed by a stack of LSTM or GRU layers, and condenses it into a context vector. The decoder starts from that context vector, and at each step predicts the next word in the target language sentence using another stack of LSTM or GRU layers. Each output token is fed back into the decoder at the next time step. You can use teacher forcing to feed the actual correct previous word during training. You can build this model using TensorFlow Keras or PyTorch. Both libraries support this structure natively. Training the model with your data. Compile your model with a suitable loss function such as sparse categorical cross-entropy and use an optimizer like Atom. Train it using batches of sentence pairs. At each batch, the model tries to predict the target sentence from the source sentence, and you compute how far off it is. You'll train for several epochs, checking how the loss decreases. Use validation data to monitor performance on unseen sentences. Make sure you save your model weights regularly and visualize training with tools like TensorBoard or Matplotlib. Evaluating the translation model. Once training is done, test your model with new input sentences in the source language. Use greedy decoding or beam search to generate translations word by word. Compare your generated sentences to the actual human translated sentences using metrics like BLEU, Bilingual Evaluation Understudy Score, which measures how many n-grams overlap with the reference translation. Keep in mind that exact matches aren't always necessary. Meaningful paraphrases might score low but still be accurate. Improving and scaling. As you get better results, you can expand to using attention mechanisms, which help the decoder focus on specific words in the input sentence at each decoding step. Eventually, you might move toward using transformer-based models like the ones behind GPT or BERT. Hugging Face Transformers makes it easier to build and fine-tune such models using pre-trained weights and large datasets. At larger scales, you'll need more hardware power, distributed training, and more sophisticated pre-processing, but the foundations you've built here remain the same.
If you're enjoying the content, go ahead and hit that subscribe button, drop a like, and leave a comment. I would really appreciate it. I love hearing what you think, Hank, and your support helps the channel grow big time. Thanks for being here. It means a lot. Let's keep